I'm moving away.
Share screen.
I'll travel the furthest.
I'll try with
Travel for that.
no. Okay.
You need to go far east for your next.
Oh my God.
I'll try.
No one ever knows that.
I need the place when we're speaking like for no offering
Singapore. Go to Chile.
because I'm gonna figure out if they speak Chinese.
Go to Argentina, you can get your 4 years of study and like
One.
$6,000.
Oh, I was even like in one.
That would have been nice.
I could have done that in France.
Yeah, you could. You should say that.
I-
Somebody that was
My brother
Your
thinks
brother,
it's cool.
yeah.
It's $600 a year.
a year.
Okay, guys. We are going to talk today about interception and infiltration. And I don't have a ton of lecture material today, so we're going to talk about the next part of the project as well. This is all for the next unit, so this is unit 2. Not on the exam next week,
What's that?
Thursday. Is it Tuesday?
The test on Thursday.
Test on Thursday, reviews on Tuesday.
We
Yeah.
already did.
Yeah, and I'll probably record something for that, so we won't have it. You can just look it up, and maybe I'll do a little office hour during class. So if you have any questions, anything you want to go over specifically. Great, so interception first is dealing with trees, grass, whatever the case may be, plants, vegetation, intercepting rainfall. So we have precipitation coming down out of the sky. It hits trees, it goes in the leaves, right? It runs down the trunks. Let's see if I can quickly change my, all right. One of these days I'm gonna have a drawing app that is actually nice. It runs down the trunks and it hits the grass. We have litter, like leaves and whatnot on the soil. And a lot of this interception, what ends up happening is it basically holds that water and it evaporates. So it never actually makes it into the soil. So whatever rains and hits all this vegetation and trees, only part of it makes it into the soil and actually infiltrates. So that's what interception is, and there's just the idea of it. And so you can think of it as like temporary water storage.
That's infiltration rate.
This is interception. And like I said, intercepted water, maybe it's slowed down a little bit. So it slows down infiltration, which is nice. We want to, you know, say it rains an inch in a couple hours. That's a lot of rain. We want to slow that down so we don't get this huge runoff wave, right? So it's nice to have stuff on the ground to intercept the water, slow it down. It has to take a longer flow path, right, as it goes down trees and on grass blades and stuff like that. So it slows down infiltration, but it also reduces infiltration from evaporation or via evaporation. And so you can imagine a little droplet on a blade of grass right here. If it doesn't hit the ground, based on the humidity and wind and everything, it might just evaporate. In the grand scheme of things, this evaporation, if something evaporates off of a leaf, it's going to cool that leaf down, and it's also going to increase the humidity near that leaf. And so the water lost to interception from evaporation, so I'll just say interception, evaporation, often offsets transpiration. And so you end up in many cases as no net change in the water balance. So what would have been transpired by the plants is offset by just the evaporation off of the plant surface. Regardless, when we're thinking about storm events, we typically don't account for evaporation because it happens at a slower time scale than the runoff flood producing processes that we're going to be talking about later. So we often neglect these things, but I just want to introduce the concept. And we care about interception not from a design storm standpoint, but more from a soil conservation runoff reduction, water quality, kind of an environmental standpoint. We'll talk about urban runoff later, but if we've got rainfall hitting just pavement, my little car, that's Dylan's car, it doesn't have a roof on it. Just kidding. If it hits pavements, then it's going to pick up all kinds of contaminants, pollutants. It's going to run off very quickly. If we've got a natural surface where the soil isn't compacted and you've got leaves and stuff like that, it's really nice, then we're going to have a nicer situation. And I'm pretty sure I have some slides. I'm going to pause this super quick. So here's a nice figure, and I'll post these slides. You've got rainfall coming in. You've got different mechanisms. T is for through fall. This is, come on, man. Anyway, through fall, we've got stem flow. You've got loss from evaporation. And then finally, you have what infiltration that goes down in. This would be loss from the canopy, that sort of thing. All right, we'll talk about infiltration now and just kind of the overall process, and then we'll kind of get into some conceptual diagrams of how infiltration rates change with time depending on soil. So infiltration is happening via gravity, right? So water is pulling, gravity is pulling water down into the surface. When water hits the surface of a soil and it's not evaporated from that through interception, then it's going to hit the soil and it's going to enter the soil via capillary action, right? You've got that suction of the pore space and then gravity. So gravity is pulling it through. And that profile and the rate that water infiltrates into the soil is going to depend on the soil texture. We learned about how clays tend to hold onto the water more readily. They also infiltrate more poorly. And you probably know that intuitively, maybe from experience. It's hard to get water into clays, right? It's going to run off more readily. Loams is kind of that in between. And then sands, they're going to have high infiltration rates. Water is going to move more quickly through them. So that's capillary action. We also have what's called macro pores. And we don't consider these explicitly in engineering applications, but they're actually very important for understanding how water moves through soil. These are things that these little critters create. We've got worms, moles, bugs, roots. Maybe a tree has a big root and dies, and then that root decays away, and you've got a lot of pores in there. These are things that develop naturally over time when you don't have a lot of cars driving over the dirt and compacting soil and stuff like that. These pores are preferential flow paths in the soil, and if they connect over distances, then you can actually have water move and infiltrate more quickly into soils because of them. So these from a scientific standpoint, from understanding how water moves through a soil column, macropores actually play a really important role in that. Resulting in, when we look at runoff response processes, when rain falls on a soil that has a lot of macropores, kind of more natural types of watersheds, you get actually faster runoff, not surface runoff, but you get more runoff than you would expect more quickly because water is moving actually really quickly through these macropores. So they can change the hydrograph. Let's just look a little bit more about soil in general. Soil has a lot of different horizons or layers associated with it. It's kind of like a cake. And you can see them outside spreading a bunch of topsoil, right? For that project, the reflection area. They've done a bunch of excavation and disturbance of the soil. They've gotten down into the B horizon, mineral rich, right? Not a lot of organic content. Maybe even the C horizon, where if you get deep enough, you get into weathered bedrock, regolith, that sort of thing. This is where it's kind of like chunky stuff, really hard to dig through. This is actual soil, right? It's got grains. The A horizon and O horizons are going to be part of the topsoil. This is high in organic content, and that organic content can hold moisture more readily, and is obviously needed if you're going to put a bunch of grass and trees down. O is the organic horizon. That's actual just like leaf litter and stuff like that. Okay. I'll just talk about this slide and then I'll get into talking about infiltration from a conceptual level. So we've got here some hydrographs. So rainfall over time, rainfall intensity on the y-axis, time on the x-axis. And we have a series of rainfall events. So the first one was a total of 2.3 centimeters. The second one was a total of 1 centimeter. And the third one was 1.5 centimeters. And this is showing you the runoff hydrograph. So the units are centimeters per hour. They just divided by the watershed area. And then we see the infiltration rate in the soil. And so what you see here is, we'll look at the infiltration rate first, is when it rained on the soil, we had a pretty high infiltration rate initially. Does anyone know why that might be initially, and then it slows down over time? You become more saturated. So that pore space fills up, and the infiltration rate slows down. So initially, when you have a drier soil, you've got a higher infiltration rate, and then that's slowing down over time, kind of this exponential decay. And so the runoff hydrograph is going to change as a function of time and the moisture in that soil. Remember I was talking about soil moisture as that master variable, right? It really controls a lot about the runoff response. And so initially we get 2.5 centimeters of rain, you get a tiny little hydrograph because most of that water is going into the soil. But then as you go, even if you get smaller rainfall events over time, that runoff response increases, becomes more peaked because we're now infiltrating less water over time and we get more runoff then. So greater percentage of that precipitation is converted to runoff. This is called a nonlinear response. What it means is that for a given input, you can get potentially different outputs. And it's not always going to be the same. So this is kind of important to know from a conceptual level. You're not going to know exactly what your soil moisture is in your basin, but maybe you can make a conservative assumption and say, well, if I'm going to model this storm event over my watershed, do I want to assume dry conditions or wet conditions to get the most conservative estimate or peak discharge? Edgar, what do you think? Just if I want to, get the upper bounds of the potential peak discharge, right? Yeah. So when we get into the kind of actual process of modeling this, you can make some assumptions. And one of the more conservative assumptions is that you have pretty wet soils going into the storm event. All right. And this is just another way to think about that. We'll look at this one first. So here's our infiltration rate on the y-axis and time on the x-axis. And so the initial rainfall is happening over time. We get this steady infiltration rate, but then something changes where we've hit some threshold and then infiltration rate reduces. And so this is a situation where the rainfall rate is actually less than the infiltration rate. So whatever's falling on the ground is getting soaked up. And then at some point we hit that, we kind of saturate the soil enough so that the infiltration rate reduces below the rainfall rate, and then runoff occurs. You're still infiltrating, but at a lesser rate. And so now whatever's raining in excess of the infiltration rate runs off and turns into flow, like surface flow over the soil. What this graph is showing you is the surface, the moisture content as a function of depth. So if this is the initial soil moisture, this is your saturated soil moisture. Initially, as you go down, you're pretty dry, and then you kind of wet up, right? With as you get closer to the surface. But it's raining, so you're getting closer and closer to saturation. It's raining, closer and closer to saturation. At time 4, we hit saturation. Now we are starting to cause runoff, and you can see this is kind of the moisture front basically going down through the soil column. So here we're saturated at this depth. Now we're saturated at a deeper depth, saturated at a deeper depth, and that saturation front moves down. So that's what's happening inside of the soil column. Okay. I'm going to just draw this a different way. So infiltration. We're just going to go with this red. I'm going to get this whiteboard working out one of these days. So infiltration, inches per hour, centimeters per hour, right? These are the units that we'll be working in. Depth over time, or length over time. So our infiltration rate, as we talked about, it's going to be a function of many things. So the first and foremost is the soil texture. What's called antecedent soil moisture. The soil compaction or porosity. Vegetation or land use coverage. And also rainfall duration. Or we could just say time, right? So like the rate is a function of time. If we're raining for hours and hours and hours, the infiltration rate is going to change dramatically and maybe even go down to almost 0. There's a great study that I learned about in grad school that talked about, or they studied, hey, how's it going?
Sorry to bother.
Yeah, come
Can
on
I
in.
just leave here something?
Yeah, sure.
This is for you guys. So we put this in for the printer. Sorry to bother.
Yeah, no worries. That looked at rainfall runoff responses and watersheds, and they were comparing kind of an urbanized watershed and a more forested watershed. And so you had a big rain event, say the 100-year rain event, right? So it's a ton of rain. And what they found was that, in a forested watershed, you'd expect the hydrograph that comes out of there to not be as big as the urbanized watershed, because you've got all these paved roads, less infiltration, most of the water is just running off these parking lots and stuff like that. And we'll get into what that looks like in a minute. But what they found was that as you go from, like, say, a 50% AEP rainfall event to a 1% AEP rainfall event, so you get a much bigger rainfall event, the difference in hydrographs, originally it's the forested watershed is going to have a lower peak discharge coming out of it than the urbanized watershed. But as you go to those bigger storm events, the urbanized watershed and the forested watershed start to look the same, because that soil gets so saturated from the bigger rainfall events that it just acts like pavement. And whatever rainfall lands on that wet soil is just going to run off like it would on pavement. So for these really big flood events, and this isn't everywhere, this was this particular study, the difference between a forested watershed and a urbanized watershed is going to be not that much for the peak discharge for that runoff response. All right, so we'll just kind of draw this a little bit conceptually. Here's some soil, we got a nice tree, we got some grass. We've got, this is not to scale, guys, a macro pore from a root or something like that. And we've got little raindrops falling down. And they're going to hit the soil, they're going to go in to the pore spaces of the soil. They're going to go into these macropores and then fill in the pore spaces along the macropores. And they're going to go down by capillary action and gravity. It's going to go laterally from capillary action. And then it's going to go down here from gravity as well. So we've got these different forces essentially mediating and enhancing infiltration. So big picture, we care about infiltration because infiltration influences, it influences the runoff response. And really what this means is the volume and peak discharge. These are kind of two key design variables that we want to know. We want to know from that storm event, eventually all that water is going to leave, right? It's either going to evaporate or run off. But over the kind of shorter window, that flood response, we want to know what's the runoff volume and peak discharge, as well as timing. How long is it going to take for that peak discharge to hit after it starts raining? Just going to use this whiteboard for now because it actually works. Okay, so let's take a look at a soil column. Here's a little piece of soil here, and we've got rain coming down at 1.5 centimeters per hour. And say this soil can infiltrate, the infiltration rate of this soil at this time is 1.5 centimeters per hour. So we're good. So whatever is hitting this soil is going to infiltrate. And that's it. It's good. The soil's getting wet. But then the rainfall rate increases. And all of a sudden, the intensity increases. And we get 2.5 centimeters per hour. Now we're getting some more rain. We're exceeding the capacity of the soil. So we're still infiltrating 1.5. And then we're generating runoff now. So we get runoff. So this is infiltration. And now we get runoff. And that's going to be 1.0 centimeters per hour. So just the difference. Just the arithmetic difference between what's falling and what's actually infiltrating. So you can imagine over time, you could develop a hydrograph by understanding, does the infiltration rate changing over time, or do we consider it's constant? And then you could understand your runoff over time as a function of whatever's not infiltrating. Let's look at some conceptual relationships for infiltration. Can I move this? Yes. Okay, so on this axis, we're going to have of infiltration rate, centimeters per hour. And then we'll just have time. This will be time after rainfall onset. So after the beginning of the rainfall. And this is arbitrary. I mean, I could make some numbers up, 6, 4, 2, 0, something like that. So we'll look at a few different relationships, and the first one is the soil texture. And we've looked at a graph like this similarly, but we'll look at one. So this could be one where it's initially high, and then it kind of slows down and starts to become asymptotic at some finite rate. And this would be for like a coarse soil, like a sandy soil. If we had a finer texture soil, maybe it starts a little bit lower, and then it's going to go down to maybe 0 or close to 0, something like that. This could be a clayey soil. So soil texture is a really important driver. And we'll talk about how we evaluate that typically when we do hydrologic modeling.
How come it tapers off like that? Like how come it kind of plateaus like that? Like the thing with a clay soil, it's always going to infiltrate, but it's at a really low rate then?
Yeah, and so maybe there's this little window where you get a higher infiltration rate at first, but that's going to quickly fill up and go down to this kind of low level baseline rate. And maybe it's close to 0 for like a super clayey soil, right? It could be 0. I mean, it might just be that it's like totally saturated and everything's going to run off after that point because the infiltration rate is so low. And this would depend on the intensity of the rainfall event too, right? So this is kind of all hypothetical stuff. It's just relative relationships. Okay, let's look at another example. And this would be for, we'll call it land use. And then we could say it'll be kind of similar lines, but maybe this would be a kind of a forested watershed. And then maybe we have something that could be something like, we'll say heavily grazed or urbanized, something like that. In these cases, that maybe the soil doesn't drain as well, maybe it's compacted. you don't have those macropores at porosity. And there's just less potential to infiltrate.
What's the top one there?
Forested. What do you guys think this would look like for our Pine Gulch watersheds over there after the fire? Yeah, I mean, it might not even, you might not, for a forest fire, I don't actually know, but it might just be like, right. It might act like pavement. And that's because because you have that hydroscopic kind of chemical response, water actually beads up on the soil, and it's not even getting to infiltrate because it's being repelled by the change in the kind of the soil chemistry at the top.
How long does it take for that to go away?
Several years. Yeah. And when we actually, this is a good kind of segue, when we talk about treatments for forest fire, I don't really have anything to draw here. You know, we talked about they dump mulch, right? They'll dump, and that's going to do two things. One, it's introducing carbon into the situation, which can change the hydrophobic properties of the soil. So once you get kind of leaching from that wood and the mulch, it'll change the chemical properties of the soil. That's one thing. And the other thing is that the mulch acts as, you know, if we think about it, it's just kind of like sticks and bark and whatever, and hay, it acts as an interception mechanism. And so maybe we don't get infiltration as much because of this chemistry issue here, but we're going to get some interception. And so when it rains, basically we're just trying to reduce the runoff that happens. And so mulch could provide that. We don't have any trees anymore, right? Everything got burnt, but at least we have some ground cover that can aid in that response. Yeah, so you could imagine like a stick on some soil is going to break up the flow path versus everything's been burned and water can just run willy-nilly wherever it wants.
So here in the spring, where they do like burning, is that only like on the wheat section and not in actual like farmland?
Oh yeah. Well, so I mean, people burn ag fields to get rid of. I mean, I'm not a agricultural producer, so I don't actually know. They burn ditches to clear ditches out. They'll burn fields because I think it releases nutrients, and I'm making stuff up here. And it, like, you know, it makes it easier to till for the next season. I don't know. Does anyone know why they burn fields?
One reason is after their last cut, and they still get whatever they're growing grows, and then that's not gonna grow. That dies, and then it stays there on the ground. So then whenever you do your first cutting, first of all, it reduces how much new stuff can go through it, and then second of all, whenever you cut it, you're gonna be throwing in all that old hay on the bottom or alfalfa or whatever. I know that's one reason.
And you don't want that around.
Yeah, you don't want that.
Yeah.
That
So
it gets all tangled up, and the new mowers are good, but like the old sickle mowers, it'll clog them up and everything. So.
right. And because like yeah, if that's alfalfa, they're not plowing that over every year. That's a perennial crop. But for annual crops, they're going to go and disc it and plant stuff again. So what I'm talking about here doesn't really matter. And they're going to flood irrigate, or they're going to do something else. So they're going to do things that'll change the infiltration capacity of the soil. All right, so that's a bunch of conceptual stuff. The way we actually use a lot of these things kind of in the modeling framework for hydrology is what's called, let's see here, what's called hydrologic soil classes. And these are pretty simple. It's so it's Have you guys seen this soil survey? NRCS, Natural Resources Conservation Service.
Look them up in geotech.
Okay. Yeah, I might have you guys do that for kind of a future assignment. But basically, almost every county in the whole country has a soil survey. And what they've done is they go out and map soils, soil types based on topography, parent geology. They'll actually go out and do some sampling and stuff like that. And so they'll classify soils based on a bunch of different things: texture, you know, the one that we're interested, so like drainage or hydrologic class. And then they'll tell you, you know, how good is the soil for agriculture? Is it prone to flooding? Is it structurally sound for different kinds of uses? All these things. But really what we want to know is this hydrologic soil class, which tells us the runoff generation potential. Basically, infiltration capacity, right? It can also tell us where we might have more or less luck with infiltration galleries, septic systems, and the like. So there's 4 different classes: A, B, C, and D. And A is going to be what we call well-drained. Sandy soils. And we have a high infiltration capacity. And we have a low runoff potential. And then we go all the way down to D. Well, I guess I'll just give you the names real quick. We have a silt loam. And these are called moderately well-drained. C, we get a sandy clay loam. And moderately well-drained filtration rate. And then D is a clay loam or a clay. Also known as poorly drained. You know, you could imagine a farmer is looking this up and they're looking at a field, they look at the soil survey and they see it's poorly drained. They're like, well, is this what I want? Do I want to deal with a poorly drained soil? You know, you got a bunch of issues when it comes to that. So we'll use these classes later to understand the runoff generation potential of different soils. And as you can imagine, since it's been mapped, you can pull up GIS data for your watershed and figure out what percentage of soils are A, B, C, and D, and then use that to help figure out how much runoff potential you have. All right, so let's review. We'll do a little kind of pop up. Give me, Jake, something that influences infiltration rates. Land use. And how does land use influence infiltration rates?
Infiltration rates are lower for urbanized area and higher for forest areas.
Right, so the less disturbed the soil is, the more time plants have gotten to grow and critters have kind of fluffed it up, it's less compacted. So you can infiltrate more. Dylan, what's another example of something that affects infiltration rates? Yeah, well, that works. What's the mechanism for vegetation influencing infiltration rates?
Full of interceptors.
We intercept. Yeah.
So the interceptors are taking some of the water that the ground would be infiltrating, but it's not. And they might eventually infiltrate it, or it's going to just evaporate and it doesn't make it to the ground anymore.
All right, great. Agar, can you think of one for me?
Texture.
Texture. Great. What about soil texture?
It's like really, it's gonna have a lot of runoff and not infiltrate well, but if it's really sandy, then it'll infiltrate at a high rate.
And why will it not infiltrate well for a fine textured soil?
If it's more compact, right? But the water actually can.
Yeah, so it's more compacted. You have less porosity, right? And the pore structure is different in a clay because you got those plates. You don't have these kind of big holes that can suck the water into them, right? Great. Christian, can you think of another one?
Rainfall duration.
Great. Yeah, so what about duration?
Depending on how the soil infiltrates, you'll get, or how much rain depends, like how much infiltration depends on the rain and how fast you get to that point where you reach max infiltration or close to it and start being run.
Yeah, so when you meet, so I see think of two things. One is you're filling the soil up, you're getting to that threshold, right, of saturation, and infiltration rate drops way down once you get close to that. And then, yeah, just infiltration rate decreases over time with soils as they become wetter. Val, you get the hardest one because everyone's taking the easy pickings here. Can you think of another example? Right, so if I go out to this construction site where they've been driving trucks back and forth for weeks, I'm gonna have high runoff potential. And versus maybe the lawn right in front of Confluence, it's had a couple years to expand, the porosity has increased over time, that sort of thing. Great. I'll see if there's anything else I want to add to that. How wet the soil was before it started raining, antecedent soil moisture conditions. And that's about it. That sounds good, guys. Yeah.
So for the soil texture, like the sand and clay are obviously opposites. I remember reading that the capillary rise is a factor in there as well. Is that only when the water table is really low? Is that when I'm talking about that?
So capillary rise happens when you have an interface with the water table.
Right.
So if you have a water table that's super close, that could be another thing. If you have a water table that's super close to the surface of the ground, then that capillary fringe could actually come up to the surface of the ground, right?
If it's like clay and has small porosity.
Yeah, and
Small channels to go up.
or if it's a wetland, right, and you're kind of close to that wetland, you could be, that's why when you have a high water table, you have problems installing septic systems and stuff like that because, well, A, you don't want to have the septic system go directly into the water table, but B, you've got low infiltration rates near the water table.
And so, like, capillary action, the rise is higher for clay, and infiltration happens through capillary action. Is the rate?
I see what you guys are saying. Yeah, let me just draw this real quick. Clear. Okay, so if we look at, let's see. We'll call it capillary action. And we talked about last time how if you have a thinner straw, oh God, that was terrible. If you have a thinner straw, let's see, I'm not going to do it better this time. Okay. The water will rise higher than a thicker straw or a wider straw, right? So because that's just the way capillary action works, we can go back to hydraulics and talk about why. And so this could be clay and this could be sand. So this is what you're getting at, is like it's higher. So if you have a clay, the capillary fringe is going to be higher in a clay than it is a sand, because you got those narrower straws that draw the water up higher into it. But that's going to happen slowly over time. So you can imagine if you had a big old pile of sand and a big old pile of clay, and everything was fairly well consolidated, and you flooded it, right? What would happen? Well, the capillary rise would happen pretty quickly in the sand. You would see that capillary fringe. In the clay, this could take days to achieve this. Does that make sense? And so that time frame gets at the infiltration rate. But at the end of the day, yeah, the clay can hold more water than the sand can for longer. It just happens more slowly. Can clay hold more water, like from a unit volume perspective? Like if you have a cubic foot of sand and a cubic foot of clay, can you actually get more water into that clay? I don't know the answer to that. I'd imagine that because sand has a higher porosity, you could actually store more water in the sand. But granted, more would drain out from gravity than would from the clay. So I don't know the answer to that, like water holding capacity question. So yeah, there's some kind of, I wouldn't say counterintuitive, but some kind of countervailing things that happen in these different soil types. All right. So that's an introduction to infiltration. We'll get into more mechanisms next time. And then we'll get into actually runoff processes. So this is kind of like the intermediate step. We've talked about rain. It hits the soil, stuff happens, and then we get to runoff.